some of the other earthquakes reviewed in this study, the structural damage resulting from this earthquake event was relatively limited. On December 7, 1988, an estimated magnitude 6.9 earthquake struck the Spatak region of Armenia. The city of Spatak was built upon relatively loose, saturated alluvial sands, sandy gravels, and gravels. The earthquake completely destroyed the city of Spatak and is believed to have killed over 25,000 people. It is believed that poor structural construction coupled with the stratigraphic conditions led to catastrophic destruction. Much like the Fukui quake in Japan, liquefaction of gravel was observed where less permeable topsoil capped sandy gravel and gravel subsoils. Yegin in 1994 goes on to conclude that the gravelly soil deposits of Spatak that were not confined against drainage could withstand large, roughly half to 1 g, peak ground accelerations without liquefying. However, a mere 30 centimeters thick impermeable topsoil could impede drainage, thus causing liquefaction of such soils, leading to significant deformations and lateral spreading. On September 21, 1999, an estimated magnitude 7.3 earthquake struck Chichi, Taiwan. The quake resulted in the death of nearly 2,500 people and caused nearly $10 billion in damage to the infrastructure of the area. Much of the damage was attributed to the severe liquefaction of loose saturated soils of the area. Most of the liquefied soils observed in the Chichi area were sandy soils. However, in the nearby Wufang and Nantou areas, gravel and gravelly soils were observed to have liquefied. Zera, 2004, observed unique geologic structures within exposed Quaternary age sediments in Brazil. The sediments consisted of braided channel conglomerates. The structures observed were sediment dikes, pillars, and pockets. These unique structures were interpreted by the Zera to be fluidization and elutriation structures created by the rapid escape of pore fluids and sediments during liquefaction. It was further postulated that this liquefaction was likely triggered by large-scale seismic shaking triggered by a great seismic event. Evaluating the liquefaction potential of gravelly soils is not straightforward. The liquefaction of sandy soils can be quantified quite quickly and accurately with the use of standard penetration tests and the cone penetration test. However, these tests are not considered to be reliable for assessment of liquefaction potential of gravel because large gravel particles may interfere with the normal deformation of soil materials around the penetrometer and misleadingly increase penetration resistance. In recent years, several studies have been conducted to investigate alternative methods for assessing the liquefaction potential of gravelly soils. Some of these methods are discussed below. To avoid the misleading interference of gravel class on the penetrometer, one idea was to use a large diameter casing driven by a diesel pile driver. This method is known as the Becker penetration test. For the test, a 168mm diameter, 3-meter long casing is driven into the soil strata using a diesel-powered double-acting pile driver. The VPT resistance is the number of blows required to drive the casing 30mm. Harder and Seed in 1986 developed a preliminary correlation between VPT and SPT results so that VPT results might be used in the accepted liquefaction equation. This initial correlation is quite varied and inaccurate in the range of 0 to 30 and 60 blows. To correct for this variance, Harder and Seed developed an energy correction procedure to correct for differing bounce chamber pressures. Using this correction provided relatively reliable results. Additional studies by Tsai and Campanella in 1994 and Lin 2004 used instrumented casings to further refine the correlations by Harder and Seed. However, the results did not appear to increase the reliability of the correlation by an appreciable amount. Adrius and Stocco in 2000 used shear wave velocity measurements from the field and earthquake data to develop a relationship between seismic shear velocity and the cyclic resistance ratio. This relationship was determined to be reliable for use with earthquake magnitudes less than 7.5 and only in Holocene uncemented soils. The shear wave velocity method is thought to be a good method for use in gravelly soils because with it, you don't have the intrinsic impediment of a penetrometer by the gravel class. The disadvantages with the shear wave method are that samples of soil are not obtained for visual classification, and without such samples, one cannot discern whether a soil is liquefiable sand or a low-density non-liquefiable clay. Seed in 2003 advocated the use of the short interval SPT test for assessing the liquefaction resistance of gravelly soils. The short interval test is conducted much the same as the standard SPT test, but blows are counted in 1-inch intervals rather than 6-inch intervals. Blows per 1 inch are plotted by the logger, and the transition from low blows per inch to high blows per inch are interpreted to be interference of the penetrometer by gravel class. These high counts are discarded, and the remaining counts are summed and scaled 12 inches to calculate a normalized blows per foot in gravel using SPTs. This method was empirically developed by calibrating SPT results of over 200 boreholes in gravelly soils. The downfall of this method is that it is only applicable in soils that contain 50% or less gravel-sized particles. Since obtaining samples of soils with an SPT sampler within a downhole boring is troublesome, determining the in-situ gravel percent can be difficult and unreliable. Flynn, in 2004, prepared reconstituted field samples from previously liquefied gravel soils from the Chi-Chi gravel liquefaction site in Taiwan. These reconstituted samples were tested in a cyclic triaxial shear apparatus to obtain an estimate of the in-situ cyclic resistance ratio of the soil. The results of the laboratory testing were compared to back-calculated values of CSR, CRR, and factor safety values for the 1999 Chi-Chi earthquake. The results of the laboratory testing compared favorably with the back-calculated results, the results from seismic shear wave testing, and conditions that are observed in the field. The shortcomings of this method include obtaining a large enough sample to reconstitute a representative field sample and being able to reconstitute the sample back to in-situ conditions. Chang in 2002 proposed the use of an in-situ dynamic method to predict the liquefaction potential at a site. The proposed method involves the use of a vibro-sized truck to produce strong ground motion at a site and instrumentation to record the ground response of said motion. The instrumentation includes embedded geophones, surface accelerometers, and embedded pore water pressure transducers. To conduct the study, a circular concrete loading footing is installed at the ground surface. A steel loading frame is installed upon this footing with a steel loading plate, and the vibro-sized truck applies its vibratory load to this loading plate. As this method is currently in the development process, it has only been used in a 1.8 cubic meter test pit of reconstituted soil installed near the assembled loading apparatus. From the initial study, the collected data was subjected to various numerical simulations, wave equations, and finite element analysis to study the effects of seismic loading and liquefaction within the test pit. While this method has not yet been applied in the field, the potential for liquefaction resistance are quite profound. The use of a dynamic method should be able to provide more reliable results for a site-specific study than has previously been available. In conclusion, we have looked at several different conditions under which gravelly soils can liquefy and which gravels are most susceptible to liquefaction. We have looked at a number of historic and geologic examples of liquefaction of gravelly soils, and we have looked at several different methods for evaluating liquefaction potential of gravelly soils. Thank you.